Okay, let's get started. So last time we were talking about transport phenomena or mass transport, things like that, and I had shown basically just wrote the equation for what's called Stefan Maxwell diffusion, where you have this sort of very complicated expression uh, that includes Fickian diffusion, barrow diffusion, Serre diffusion, and unequal body force diffusion. Where these DIJs here are the binary diffusion coefficients, uh, and these DTs are thermal diffusion coefficients. And then there's also a heat flux vector when you have multiple species that are diffusing into one another. You need to account for the traditional heat conduction. You also need to account for the energy that is being transported with the different molecules as they are diffusing around. And also there is a second order effect that there's a heat transfer due to mass diffusion. It's a second order effect and normally quite small. And in the driving potential that's used to compute the diffusion velocity, it's often given like this in this form here. So this does include the effects of barrow diffusion. Okay, and we ended off discussing what the Serre effect is, and it's just and it's not really that well understood for gases, but I did give an analogy called thermophoresis for particles. Um, okay, so now we're going to move on, and now that's Stefan Maxwell treatment. That's really expensive to use, because one of the reasons it's super expensive to use is that um, say you're at a point in space and you know at that instant of time you can compute the gradient of the mole fractions, but even if we neglect all of these terms here and we still have the Fickian diffusion, but what you want are are basically all of the diffusion velocities, but all of the diffusion velocities are coupled to the gradient of xi, and so then you have the gradients of all the mole fractions. So basically, this forms a system of equations that you have to solve, and so it's not explicit in terms of just computing the diffusion velocity, which is what you want, in terms of the properties of the flow. And so it's very accurate, but it's very expensive to use. Um, and so instead, there's so-called mixture average transport. It's an approximation to the full multi-component or Stefan Maxwell transport, and it's a cheaper alternative. And essentially, what you do is you define the diffusion velocity to be some mixture averaged mass diffusion coefficient. This is no longer a binary diffusion coefficient, so we need to compute that over the mole fraction times a diffusion potential. And if you want to include the Serre effect, you can. It's not very commonly done, to my knowledge, with mixture averaged. So normally the mixture averaged diffusion velocity is just given like this. Now note I have the reason that I have a tilde here will become apparent in the bottom of this slide. And then here there are multiple definitions for the mixture average diffusion coefficient, because it's not an exact theory, it's an approximation, and there are a variety of different approximations for this mixture average diffusion coefficient for species I. The one that is traditionally used in combustion is defined as such, and in your guys' homework you will be actually deriving this expression. Um, okay, and it's based off the binary diffusion coefficients. Um, Now, one problem that you need to consider with if you use mixture average diffusion coefficients is that conservation of mass, the sum of rho yi vi, that needs to be zero, because again, mass diffusion can induce zero bulk flow into the system. So that means there is no net mass transferred by basically mass diffusion. That is, if I have a system boundary and I have hydrogen over here and oxygen over here, for every kilogram of hydrogen that moves over here, I have a kilogram of oxygen that basically moves in. Okay, and so what we do is we define a corrector velocity such that the final diffusion velocity that you use to compute the mass transfer is this mixture average diffusion velocity plus a corrector velocity that is constant for all of the species. And you can show by enforcing this property here that this corrector velocity is minus the sum of the mixture averaged predicted diffusion velocities times a mass fraction times the representative mass fraction. And you basically tack this on to basically all of the mixture average diffusion velocities. And you have a basically transport expression here that is mass conservative and it's also far simpler because again, the diffusion velocity here, it does not depend on the other diffusion velocities. And so it's explicit. You just need to compute the binary diffusion coefficients. Then for all the species pair, then if you know the mass fraction and the mole fraction, you can compute DI mix. Then if you have DI mix, you can then compute the diffusion potential, and then away you go. Okay, so it's explicit. There's no equations to solve, things like that. Now, so this is and you are giving up something, but it turns out that for heavy hydrocarbons, with the exception of maybe hydrogen, this is actually fairly accurate, and it's accurate enough for most applications. There are certain things where it's probably not the best, maybe for hydrogen, but still folks use it anyways. Okay, so now there's a question here. I keep mentioning these thermal conductivities, these binary diffusion coefficients. So how are those computed? Because these aren't just values you can look up in a book, because in a reacting flow, you can have hundreds of species. They're at a variety of pressures. Like if you're looking at a detonation or an explosion event, you can have many decades of change of pressure. The temperature can basically vary between 3,000–4,000 Kelvin all the way down to say 200 Kelvin or 100 Kelvin if you're in some sort of high-speed flow facility. So there's a wide range of temperatures and a wide range of pressures. And so under such conditions, it's not really accurate to just look in a table and for each species just pick an average value. And that is useful for some theoretical work, but for like actual real engineering calculations, you need to use good approximations to the properties. And so I'm not going to get into this theory; it's way too advanced. In fact, I barely know it myself. But where these transport properties come from, that's the binary diffusion coefficients, etc., is they come about to an asymptotic expansion called the Chapman-Enskog expansion. I'm not going to discuss what that is, just so that you hear the term, and it's actually approximating the Boltzmann equation itself. And essentially, the game that you play is that you perform statistical integrals of basically two molecules colliding, and you keep track of different properties. And in fact, if you use this approach to the Boltzmann equation, you can derive the conservation of mass that we normally use. You can derive Navier-Stokes, and you can derive the transport coefficients, things like that. And so the Boltzmann equation itself is far more general than the standard conservation laws that we basically normally use. Now, these aren't just basically rigid. Now, when you do these collisions and you perform statistical integrals, these aren't just rigid spheres that are bumping into one another. Around each of these molecules, there is a potential force field surrounding it. And so a lot of the complexity with mass diffusion and things like that is basically how these two molecules interact when they start to get into when their potential force fields start to interact with one another. And basically, this theory is basically used to actually compute the transport coefficients for a reactive flow on the fly. And inputs to this are the so-called well depth, which is this distance here, the diameter of the molecules, and a whole slew of other things. Okay. And so skipping to the end here, how this is computed. So if you want to compute the viscosity and binary diffusion coefficient for species I, you basically, this theory predicts that for a dilute gas that is an ideal gas at at fairly low or quote normal pressures, that the viscosity of species I is 5/16 times this expression here. Okay, where this Kb is the Boltzmann constant. And the Boltzmann constant is nothing more than a universal gas constant for individual molecules. So it's just Ru divided by Avogadro's number, and then that's the Boltzmann number. Okay, and basically then you divide it by here, and then all the nastiness of integrating all those collisions and things like that is baked into this integral here, and basically those are given in terms of a curve fit to the data, because basically this theory was developed in the 50s, and it's really expensive to use. So basically they just basically do curve fits to the data, and it's a function of what's called a reduced temperature and a reduced dipole moment. I'm not going to get into the physics of this. This stuff gets actually really complicated. And then there's a similar trend for the binary diffusion coefficient. I'm not going to get into that. Just sort of one thing to note is that the diffusion coefficient itself has a different temperature dependence than the viscosity. For a gas, you notice here that the viscosity increases with basically roughly the square root of temperature. This collision integral is a function of temperature, but it's a weaker function of temperature than the square root of temperature in the numerator. So the viscosity of gases increases with increasing temperature, which is opposite of, say, liquids. And the binary diffusion coefficient, oh, and there's no pressure effect here in the viscosity. But binary diffusion coefficient, on the other hand, between species I and species J is different. First, it varies by temperature raised to the third power, and it's inversely proportional to pressure. Okay. And so the binary diffusion coefficient itself is strongly dependent on temperature. But notice when we go back to our diffusion laws, what we actually really care about is not d by itself, but the quantity rho d. And so basically rho d would be just the density times this expression here. And it turns out that basically that the quantity rho d is weakly dependent on temperature. Okay. And then also one thing to note is that the binary diffusion coefficient is proportional to 1 over the square root of the mass of the molecules. And so this basically means that light molecules diffuse more rapidly. It's sort of like if you're on it just basically means if you have a mixture of big molecules and small molecules, the small molecules can basically fit between the gaps of the big, can basically have a much easier time fitting between the gaps between the molecules, whereas so they diffuse much more readily, whereas big molecules have a much harder time and they diffuse much more slowly. And that's sort of borne out if you ever work in a lab and you're working with hydrogen. A hydrogen leak is a pretty bad deal because it can diffuse everywhere really fast. So are there any questions with this so far?
Well,
okay.
Professor?
Yeah.
Couldn't you have, like, smaller particles that are more dense than larger particles?
Yes, but in the statistical mechanics, they are more massive, but their fluctuation velocity will be smaller too. So I don't know. I'm just looking at the equation here.
Okay. Well, yeah, but I'm just like, it's like we're assuming that if you're smaller, you're lighter, or like you can diffuse easier. But does that depend on the density? Like you could be,
I mean,
like,
for a traditional hydrocarbon or combustion, big molecules are heavier because basically you make a heavy molecule by taking a bunch of atoms and sticking them together. So a big molecule is traditionally heavy. If you have, I don't know, uranium vapor, then that might be a different story.
Okay.
I don't know, which is basically one atom, but it's very, very heavy. And I don't know what the molecular diameter is of, say, like uranium, which is extremely heavy. I don't know. But in general, with hydrocarbons, with certain exceptions, a small molecule is a light molecule, like hydrogen would be the poster child for that. And a big molecule is also tends to be heavy. And so isooctane is a big molecule. Okay.
All right. Yeah. Thank you.
Okay. And so again, I'm not going to go through all these theories. The thermal conductivity is actually more complicated because there you need to account for all how like molecules store energy. That is, they can translate, they can rotate, and then they can vibrate. And so you need to consider all of those, and that gets even more complicated. So it just becomes pages and pages of basically formulas. Now, if we want to extend these to high pressure gases, there is really no good theory for that to date. There have been some attempts to use the Boltzmann approach for basically super high pressures, but those haven't worked very well. And so most of the high pressure corrections to the viscosity and the mass diffusivities, etc., are largely empirical curve fits, and many are based off of the so-called extended corresponding states principle, where for any property, you can say a property psi, this could be viscosity, it is equal to the viscosity of a reference fluid multiplied by some bogey factor f. Okay. And this corresponding states principle, the original corresponding states principle, is the one that you folks may have used in that are the basis of the compressibility charts. So here's just data from a thermal book. And here they just plot the reduced pressure, which is just the temperature divided by the critical temperature. And then on the y-axis they plot the compressibility factor, and all of these different symbols are for are basically four different fluids. Okay, and so you notice that if you basically normalize these fluids in terms of the reduced temperature, which again is the temperature divided by the critical temperature, and the reduced pressure, which is the pressure divided by the critical pressure, if you normalize the data on them, you notice that the compressibility factors for all of these different fluids, basically ranging from methane to ethylene to N-heptane to pentane to water, they all lie roughly on the same curve. Okay, and so basically that is the basis for the compressibility chart. That's the basis for Peng-Robinson equation of state, of how they allow you to blend all kinds of different materials together, is the fact that basically quote normal fluids, and by normal fluid that is a technical term, basically normal fluids all mix nicely like this. Okay, And the extended corresponding states principle extends this idea to other properties. And it's the basis for a lot of empirical correlations for high pressure transport coefficients. Okay. And there's a good book by Pauling and O'Connell and them called The Transfer Properties of Gases and Liquids, which has many, many correlations. Okay. And so for high pressure thermal conductivity, as I said before, and viscosity, there are all kinds of these. There's a paper from Chung et al., and I'll be posting these from 1988. There's one from Eli and Hanley in 1983. There's one from Lucas in 1981. That's viscosity only. And that's described in Quo second edition in Appendix A, I believe. There's another one from Zabalowi from the International Journal of Thermophysics. That one's fairly recent at 2001, but it's for pure fluids. And they do not describe how to compute basically mixtures. Okay, and so this here is described in a very recent thesis performed at Penn State, where they were modeling very high pressure combustion of nitromethane, and they needed to model the viscosity of nitromethane so they could compute a Reynolds number for their experiments. And so here's just a whole slew of equations. But at the end of the day, what they need is this basically modifies the dilute viscosities that I showed you how to calculate, and it basically multiplies them by this sort of bogey factor F, and basically this parameter here. And so this is implicitly using the corresponding states principle. And there's a very complicated curve fit, and this very complicated curve fit basically comes from curve fits through empirical data. Okay, and then when they use this to predict the viscosity of supercritical methane, or not supercritical methane, supercritical nitromethane, they can see that this pressure effect at say very high pressures has a significant impact. Here is the viscosity at 6.5 MPa. This straight line here where it's sort of going up rather gently, that's the ideal gas behavior, where the viscosity is roughly increasing with the square root of temperature. And there's not much of a pressure effect until you get to very, very, very low temperatures. And then it starts to behave like a liquid. And so you would expect the viscosity to go up massively. Then as you increase pressure, it starts exhibiting supercritical behavior, and the viscosities keep going up and up and up. And so if they were at 1,000 Kelvin for their experiments, and they wanted to compute a Reynolds number, if they didn't account for these supercritical effects on the viscosity, they could be off on the Reynolds number for their flow experiments by about a factor of 4, which is pretty substantial. And it's enough to knock it into a completely different flow regime. Okay, and so there are all kinds of these. You need to look in the papers themselves to see how they're used. Okay, and then I'll just show the viscosity one. This is the one that you most commonly see being used in supercritical combustion, is the one from Chung et al. It's not super well described in that paper, so I just basically pasted a snippet from a very recent paper from Giovanni, and again, I'll post this paper on the Canvas website. And essentially here, they define the thermal conductivity as the dilute thermal conductivity, basically based on the dilute theory or the Boltzmann theory that I showed before, plus a bogey factor, plus a high pressure correction factor. And again, all these curve fits come from the corresponding states principle. And I'm not going to go through all of these equations, but to get this lambda HP, that's this expression here, you need this B7, and it just gets really, really complicated. It's just formula after formula after formula. Okay, and so, but if you need it, it's sort of right here. These are pretty hard to chase down, so that's sort of why I'm putting these here. But I'm not going through them. There probably is a lot of physics to this, but this is not my area. So, but this is a plot from that paper where they were plotting the thermal conductivity of oxygen at 100 atmospheres. And so this line here is if you use the ideal gas limit, and if you use if you use the Chung correlation, they get a line that at high temperature it behaves like an ideal gas, as you would expect, but as you keep decreasing temperature, it goes down and down, and eventually you start to condense the oxygen at this high of a pressure, and it starts to achieve the thermal conductivity of a liquid. And basically this matches the empirical data fairly well. Okay, and then and so these are sort of very nice theories, and if you need to use them, basically when I do and basically later on after I do a lecture or two on supercritical combustion, you'll find that for like flames and things like that, all these crazy corrections usually make a very modest difference. But for some applications, they can make all the difference. And so I'll discuss basically some of those. Because again, computing all of these formulas here is actually really very expensive. So you don't necessarily want to do it if you don't have to. And then, okay, there's that. And high pressure mass diffusion requires both modifying the diffusion potential and the binary diffusion coefficients. So it's kind of a double whammy. And here you base it off of the more general diffusion potential, where it's just the mole fraction of species I divided by RUT times the gradient of the chemical potential. And this gradient of the chemical potential is evaluated at constant temperature. And also the chemical potential, and I'll put this in the notes, it must be written as a function of temperature, pressure, and also composition. And you have your choice, like usually mole fraction of the species. Okay, and so you have to base it off of this, minus a sort of kinetic effect due to pressure gradients. And if you apply this formula to an ideal gas, you get the diffusion potential that I showed you earlier. And so, but yeah, this gets very complicated for gases already. And now on top of the diffusion potential, you need to correct the binary mass diffusion coefficients, and these usually come from Takashi, where they compute a ratio of basically a binary diffusion coefficient times pressure over the binary diffusion coefficient times pressure at 1 atmosphere. And then it's just it's a fairly nice function of these different coefficients here. And so you got this reference dp ratio here, that those parameters come from this table as a function of reduced pressure times this expression here, and you got all the constants here. Okay. And where you can get the reduced temperature, or where you can get the critical properties, either from data or from actual, or basically estimated from the method of Chung. If you look in the method of Chung, is that based on, if you assume that your gas or your fluid is a Leonard-Jones fluid, meaning it follows this potential here, this does exhibit liquid-like behavior. If the molecules are so close that they're basically in each other's, if they are in each other's potential well here, but not close enough to bond, then they exhibit liquid-like behavior. And so there's a lot of liquid physics that are actually baked into these two. And so basically, if you have a species and there's no way to empirically measure a critical temperature, like it's a very unstable intermediate species that comes and goes during the process of a chemical reaction, and it doesn't exist long enough to actually measure it, there is a way to actually estimate it based off of the Leonard-Jones parameters here, based on the well depth divided by the Boltzmann constant. Okay, and so that's sort of one way that basically we can apply these formulas to all of our different species used in combustion. Okay, and there's another one that's gaining traction. It's based directly on Leonard-Jones potentials and high pressure Boltzmann-Enskog expansions. And basically this is just the ratio of the high pressure diffusion coefficient divided by the dilute computed diffusion coefficient is just 1 over gamma ij. And this gamma ij is basically given by this function here, where it's basically a function of the number density of all the different species and the collision diameters. So it's actually a fairly nice theory to use. Okay, and so these all give slightly different results because there is no basic theory. There's no widely agreed upon way to do it. Just if you work in this area, whatever you do for these diffusion coefficients, some folks ignore this complicated diffusion potential and use the ideal gas diffusion potential anyways, even though it may be inaccurate. But whatever you do, you should document it and basically list your assumptions. It's sort of because there's so many different things that you can do, and they do have impacts on your results. You should be very explicit about basically the correlations and equations that you used. Okay, so are there any questions on that? Okay, so I was just presenting data there. And then also before I close the section on transport, there are common dimensionless numbers in combustion. Just recall quickly that the thermal diffusivity alpha is just the thermal conductivity divided by rho Cp, and the kinematic viscosity is nothing more than the dynamic or shear viscosity divided by the density. And then in combustion, you'll see all three of these numbers being used. One is the Prandtl number. You may have nightmares about that one from heat transfer. The Schmidt number, it's like the Prandtl number, except for the thermal diffusivity is replaced with a mass diffusivity. And then in combustion, the one you'll see being used the most is the Lewis number. And that's just the ratio of the thermal diffusivity divided by the mass diffusivity. And I always had a hard time keeping these straight as to whether the Prandtl number was alpha over nu or nu over alpha, and the Lewis number was alpha over d or d over alpha. Ken Ko taught us a mnemonic for this. Basically, all three of these numbers either involve the kinematic viscosity or a mass diffusivity. And so just remember that it's the numerator over the denominator. And so basically, if it has a d, the d is always on the bottom. If it has a nu, the nu is always on the top. And then if you remember just which ones have which variables, then you can apply this mnemonic and basically just remember which one's which. And the other one that we'll use is called a Domkohler number. It's not based off of transport, but it's a characteristic of flow or diffusion time. And so there are multiple Domkohler numbers because of that, divided by a characteristic reaction time. Okay, and so this tells you, gives you an idea of how important it is to assume finite rate chemical kinetics. If the characteristic reaction time is very fast relative to the flow or diffusion time, you can assume that at any given point in space, your flow is in chemical equilibrium. If the reaction time is very slow, you can assume it's frozen and then also forget about chemical reactions. If it's on order 1, then that means you need to do full detailed chemical reactions and detailed transport, etc. Okay, so are there any questions on this?
Just, I guess, we went through a lot of, I guess, fairly involved equations here. When we start talking about detonation versus combustion, how important are some of these intricacies that we looked at as gases or things are at their extreme limits and their certain properties are changing rapidly from, you know, at different temperature and pressure regimes? Is it less complicated for detonation because the time scales are so much faster, or?
We will discuss that more with detonations. No, it's less complicated for detonations because detonations is extremely, or solid detonations is extremely empirical. Because you're at such extreme and rapid conditions, the equations of state are basically hand wavy empirical garbage, if you will. There isn't really much theory involved in them. The chemical reaction models, such as Tarver's ignition and growth, that's nothing but an empirical thing. It doesn't even involve temperature, which makes no sense from a chemical reaction standpoint. So one of my, if you work with solid explosives, one of my goals in this class is to get you to sort of realize that that's a very, very empirical field. With the exception of ZND and DSD theory, it's sort of cobbled together with a bunch of empirical knowledge. There isn't too much theory with it. With the exception of ZND and CJ theory, which we will discuss, and also DSD theory, those are on extremely firm theoretical grounds. But like you said, because detonations are so rapid, a lot of this mass transport does not matter. But if you're doing propellant combustion, it's extremely important. And so it depends on the the applications. So energetic materials are more than just explosives; they're also propellants. And so for propellants, you need to consider all these diffusion effects. And in the explosives community, I went to a training seminar for a code called Shamrock, which is a blast code, and they were trying to model detonations. They were trying to model propellant deflagrations using techniques for detonations, but their code didn't have thermal conductivity. And and I pointed that out, and they didn't understand because it just wasn't their area. It didn't mean they were dumb or anything like that. They just didn't know. But for propellant combustion, you need to include thermal conductivity and things like that, mainly because they happen much slower. Okay, but yeah, and so does that answer your question?
Yeah, I come from the detonation world, and I'm a little bit overwhelmed kind of looking at these transport laws and thinking, I don't see this anywhere. And, the only thing that comes to mind is that, well, we're on a different speed and time regime, I guess, but it doesn't mean necessarily that the physics should be thrown out the window.
But for the most part, in detonation, they are. I mean, and part of that is by necessity. I mean, with the exception of maybe the work that like Los Alamos is doing right now, the equations of state are all empirical based, just basically proof fits to data. That is basically all they are. And because of that, I mean, if you think about how, like, we went over these really detailed equations of state, and if you think about it, if you're using, and we'll go over what's called JWL later on, but if you look at JWL, there's a JWL model for TNT products. There's a JWL model, a different JWL model for RDX products. There's a different JWL model for Penton products, et cetera, et cetera, et cetera. So that means there's a different equation of state for all of these different, for basically all these different compounds, and you have to look it up, which from a physical standpoint, that makes no sense. Because again, the detonation products are just mixtures of basically normal gases. So in reality, there's one master equation of state that can basically mix everything together nicely. And I think Los Alamos is trying to work on one that is accurate for that. And so, but yeah, so but we'll get into that stuff when we discuss detonations. Okay, and so, but yeah, this stuff here with the transport was just a presentation of data. And now to see how they're used, we got to move on to the next module, which I'll do via normal slide or via notes. Let's see, go away. And that is, we are going to discuss the governing equations.
Professor, will we have these given to us, or should we be writing these down?
I actually already posted them.
Okay.
And I'll be adding to them. But before I get going, is that for those who've not had Fluids 1, I'm just going to go through super quickly what some of these basically vector quantities are. Because basically some of these you've seen in your Calc 3 days, or maybe your undergraduate fluid mechanics, and some you have not. And so there's a quantity here called a dyadic product. And you have a dyadic product. If you just notice, there's a vector multiplying basically multiplying another vector, and there's no dot or cross between them. Sometimes it's written with an O times or a circle with a cross in it. And basically, I'm not going to go through what this how this works, but basically think of it as a matrix as a vector basically being multiplied by a transpose, and you tack on the unit vectors of both. And so basically, the dyadic product of A and B gives this sort of matrix here. Okay, and this thing here where you have two different unit vectors, that means it's a tensor. And a dyadic product is a special tensor because it just has some special properties. I'm not going to get into what those are in this class. I just need to get you to understand all the different vector notation, because I prefer vector notation over Cartesian tensor notation. And a very common dyad that you'll see when we start deriving the governing equations is grad v. The gradient operator is a vector given by this here, and the velocity is also a vector. And so grad v is a dyad. And so if you use this equation here, where A is the gradient and B is the velocity vector, you'll see that grad v basically just basically turns into this. Okay, so and I think most of you have probably seen that before, maybe not in vector notation, but at least in Cartesian tensor notation. And then you can, and since this is a tensor, you can take the dot product of a vector and a tensor, gives you a vector. And so if you take v dot grad v, which is a very common one that you're going to do, or that we're going to do, that expands into this here, where it's just basically this term here. And I'm not gonna read them off. Okay, then a tensor, I'm going to denote that with a double underbar. Like your stress tensor is a common tensor. You guys have actually been working with tensors all the way back since your mechanics of materials days without really realizing it. And so basically you have tau 1, and that's I hat, tau 1, 2, I hat, j hat, etc. And so this basically fills a 3x3 matrix. Okay, and so you guys have probably seen this before, maybe without the unit vectors, because they are a bit weird, but after you get the hang of them. And then also, one thing I will say about this is a left dot product, and a left dot product sort of claims this left unit vector here. It basically dots out. If you do a right dot product, if it was grad v dot v, you would actually remove the right unit vector in the dyad. Okay, and there's also something called a double dot product, and that's just a tensor double dotted with basically with another tensor, and that's just basically all of the components of A and B multiplied and added together. And so this would be like in MATLAB, if you do A dot times B and basically sum up all the entries, that basically gives you that. So it's basically A11 B11 plus A12 B12 etc., all the way to A33 B33. Okay, and so we will be using that. And some common identities are if you have the gradient or the divergence of a scalar multiplied by a vector, it's just that scalar times the divergence of the vector plus the vector dotted with the gradient of the scalar. So there's sort of a product rule for that. There's a product rule for a dyad. And so the dot product with a dyad is just A dot grad B plus B dot grad A. It's sort of, you sort of distribute the dot product. And then there is a product rule for the divergence of a vector dotted with a tensor. Because again, this whole quantity here is a vector. And it's A dot grad tau plus tau double dot grad A. Okay. And actually this should be, I'm missing a dot. There's a dot right there. A dot, the divergence of tau of the vector plus the double dot product of A. And in the back of Ken's book right here, he has all sorts of really nice properties basically listed out. And so if you're not familiar with these, you know, just bear with me. We will only really be using these hardcore in the governing equations section because they're super important. But you can find these in the back of a lot of books, and I'd like to scan that and then give it to you guys because it's extremely useful. But it is also I would be infringing on copyrights, even though Ken Cole passed away. And the book, I don't think it's going to be in print for too horribly long. Okay, and then also recall there is the Gauss divergence theorem right here, and that is that the volume integral of the divergence of a vector is equal to the surface integral of that vector dotted with the surface normal basically dotted with the surface normal on the surface of your object. And then there's the equivalent gradient theorem where the volume integral of grad P is equal to the surface integral of P n hat dA. It's just a special concept. It's just a special version of the Gauss divergence theorem. Okay, so now that we have all of these sort of vector identities out of the way, we will be using them. And for those of you who don't have experience with them, you just sort of need to basically play with them and then get used to them. But yeah, but I think most of you have probably seen them. And most of you have seen the governing equations derived about 10,000 times. And so basically, I'm going to go through this very fast. I'm not going to use the infinitesimal control volume approach. It takes too long. Any amount of time that we spend doing things like that or discussing like crazy details of like transport theory and stuff like that, or chemical reactions, like in the other combustion class, that takes 3 weeks. We did it in a day. And basically any time that we spend doing that stuff, we can't get to the fun propellant and like detonation stuff. But I do need to provide a background for that. So I'm going to use the Reynolds transport theorem approach to deriving them because it's super fast and it's very, very elegant. And it is independent of the coordinate system that you are in. So just recall there is a Reynolds transport theorem that you guys have had in fluid mechanics, either at the undergraduate level or the graduate level. And that just states that the time rate change of an extensive quantity B in your system is just the stuff inside. If you're following your control volume around in space, or you're following your object around in space, is equal to partial T of the volume integral of basically rho B dV plus the surface integral of rho B V minus VB dot n hat dA. And where v is the fluid velocity vector and v is the boundary velocity of basically your object. And so this surface integral term here represents the net transport of B moving through the surface. So you could have B moving out through here. And basically this is accounting for, and this VB here accounts for the fact that your boundary may be moving, or the control volume may be becoming bigger and smaller in size. And in this class where we are not going to mess with that, maybe technically we will a bit when we do multi-phase flow. But for those of you who want to model like internal combustion engines using CFD, as the piston goes up and down, you will be dealing with control volumes in your CFD code that does that, that basically get bigger and smaller. And so for engine guys, or if you're working on like gas turbine blades and you have spinning gas turbine blades, you will have moving control volumes in those types of scenarios. So I leave it here in a fairly general term for that reason. And so this term here represents the accumulation of B in the control volume. So then on Monday, we will start applying this Reynolds transport theorem to derive the governing equations. And I'll be posting a homework fairly soon.